Um, so we are back to Monte Carlo again. So thanks for the introduction, and also thanks for the opportunity to be able to share with you about what we have been doing. So the topic today is about understanding graphene and water non-bonding interactions from the quantum Monte Carlo calculations. Dr. Narayana Aluru is a PI and also my advisor. And Dr. Lucas Wagner is a co-PI, and he's also the main developers of the quantum Monte Carlo code we will use. And Dr. Wagner on Tuesday presented how to use this quantum Monte Carlo technique to understand unconventional superconductor. And today our focus is about nanofluidics. So water behaves differently at nanoscale. So we have a few examples here. Here the bucketball is a cage molecule composed of 60 carbon atoms, and experimentally people can do some molecular surgery to open the cage and put one water molecule in and then close the cage. Because this bucketball have a high symmetry in its geometry, so the energy barrier for water to rotate inside is very small. So experimentally they found that water can rotate very freely and fast inside this bucketball. And the second example is a carbon nanotube. So carbon nanotube is a tube composed by carbon and with a diameter of a couple or several nanometers. And because the surface of the nanotube is very smooth, so the friction between water and the surface is very small. So that's why experimentally they observe fast water transport through this tube. And the third example is recently an experimental group from University of Illinois found that they are able to manipulate water, which is confined between graphene and mica. So what they found is that these two STM image use STM. This down use STM image. So what they found is that the height of the water layers is reduced close to the STM tip when they apply high voltage. And it's pretty amazing to think about that. I mean, the water can be manipulated at such scale. So all these unique behaviors of water have promising applications like seawater desalination, the sensing, storage, and nanomanufacturing. So we'd like to have a control of these interfaces for design of all these applications. So the challenge we have is that we don't know how water interacts with this carbon surface, and we don't know what's the binding energy between water and the surface. This binding energy actually is pretty important in the sense that it determines many properties we observe in the system. So if we were able to tune this binding energy, we would observe completely different properties in this system. For example, the graphene surface can be predicted from pretty hydrophobic to super hydrophilic, and the carbon nanotube can be filled by water at one binding energy, while it's not weighted at all at another binding energy. And the water flow rate through the carbon nanotube can change by a factor of 3 at different binding energy. So definitely we want to get idea. We want to know where is the real binding energy is sitting, so that we can get a prediction of the properties we are interested about. Usually, this binding energy is estimated by measuring water contact angle on the carbon surface, on the graphene or graphite surface. But a recent experimental paper found that this measurement is very challenging because of surface contamination and also defects on surface. So what they found is that if you expose the surface in the air in clean room for only a couple of minutes. So the contact angle can change as much as 20 degrees. So that's a very huge change in estimating. In estimating the binding energy accurately. So here, so it's saying that determining this binding energy from experiments is very challenging. So we take another approach. So we are trying to estimate this binding energy by so many body Schrödinger equation. So the equation is shown here, and the X here represents the positions of all the electrons. So you see this is a very high dimension problem because, for instance, if we have only 300 electrons in the system, that will correspond to around 900 dimensions in the system. So you can consider this as solving a very high dimension partial differential equations. The psi here is a wave function, and it's related to the probability of finding electrons in some positions. And E is the energy of the system. That's a quantity we are trying to find from our calculations. And this H hat here, I don't know why it's not displayed properly. The H hat here is a Hamiltonian operator, and it composed of the kinetics of the kinetic energies of the electrons, and interaction between electrons and nuclei, and electron interaction between electrons. And this interaction between electrons is a quantity that makes the equation really hard to solve because it makes the equation inseparable. And many methods is trying to make approximations in this quantity or add some ad hoc formulas trying to replace this formula, for instance, density functional theories. But for the problem we are trying to solve, because we are interested in the non-bounded interactions between graphene and water, and that interaction is all come from the electron correlation. And so it means that in order to get an accurate energy estimate of that energy, this term has to be considered in a very accurate way. So it's for the same reason that density functional theory usually underestimates the binding energy. So definitely we have to go beyond density functional theory. So the method we are going to use is called diffusion Monte Carlo method. So it's a technique trying to solve the Schrödinger equation use Monte Carlo scheme. So here we have a little example showing how this method works. So basically this diffusion Monte Carlo maps the wave function we are trying to solve to the distribution of the workers. And it maps the kinetic operator in the Hamiltonian to the diffusion workers, while the potential energy to the birth and death of the workers. So consider a simple example that is a harmonic oscillator. And the external potential, as we know, has a parabolic shape. And here we want to use this simple example to show, how use this technique we can evolve the system and finally get the wave function we want. So we start from the wild guess of the wave function, that's a uniform distribution. And we know that this is far away from what we want. So we let the system evolve. You can pay attention to this one. And what happens is that the workers which is lies close to, where the potential is high, they are killed. And the workers lies where the potential is low, and they are giving birth. So what happens is that workers will accumulate in where the potential is low, and finally the equilibrated distribution will have a Gaussian distribution. That we know is the ground state of this harmonic oscillator. So that's how we, that's a toy problem to show how this method works. So, and we verified our method using use a small system which is a benzene, and it also has sp2 hybridization same as graphene. And we use this system to verify our method, and it performs quite well for this small system. And then we go up to the graphene, and here is where we have to use blue waters, because to give an example, one graphene water energy data point costs 200K core hours, and this calculation is impossible without blue waters. And here it shows, this figure shows how our the code we use is called QWalk. That's the code we use to perform the diffusion Monte Carlo. And you see that the code scales pretty well up to 70,000 cores, and it only deviates a little bit from the ideal case. So the reason why it scales so well is because first we are doing Monte Carlo calculation, and second, the algorithm is properly optimized to minimize the communication between nodes. So that's how we get this pretty nice linear scaling. And using with this really good scaling of this QWalk code, I mean, we are able to do, and also blue waters, we are able to, I mean, tackle the problem which tackle this, I mean, the very expensive calculations. So our simulations that used to take days to finish in other systems can be finished within, I mean, even hours for blue waters. So that's a pretty nice advance. So this, these two figures shows the configuration we will use. So one single water is sitting on top of the graphene, and we also consider different water orientations with respect to the surface, and also the separation distance between water and the surface is separated to see, I mean, how the interaction changes at this non-equilibrated positions. And this is what we have. We are pretty excited to get this because no one else have I mean, studied this graphene and water system down up to the accuracy we have been considering. So we are first in this study. I mean, with the help of blue waters. And our energy is in good agreement with the experiments, and that's pretty nice. And also besides binding energy, we can go a little bit further in from our calculations. We can go a little bit beyond just binding energy. We can understand why the interaction is so strong, and we can get some idea of. We can get some more details of how water interact with the surface. So we consider the electron density distribution when graphene and water are coming close. And before we do that, we get these energy levels of water and graphene. And what have these values are from experiments. And when we look at these values, one interesting thing is that, I mean, there is one empty water orbital which is sitting just besides the Fermi level of graphene, and also it's a little bit lower in energy. So which means when we bring the two really close, probably there could be some electron transfer from graphene to water. So we did our the electron density analysis from the quantum Monte Carlo calculation, and we did found, I mean, the case. We see that the electron density for water is positive, which means, I mean, the water is getting some electrons from electrons. So that's exactly what we, this calculation shows, I mean, so we believe that this charge transfer between a single water molecules and graphene is the reason we could be the contribute to the graphene and water interaction. So it may explain why the graphene and water interaction is so strong. So to conclude, so our ultimate goal is to control water at a nanoscale, but I mean, but as I mentioned, the challenge is that we don't know how water interacts with the surface. So with the computing power of blue waters, we are able to do very accurate calculations about the binding energy between water and surface. And also we can go beyond the binding energy to understand a little bit more about why the interaction is so strong and whether there is charge transfer between water and graphene. So we thank our founding agent NSF, Air Forces, and also College of Engineering from University of Illinois for this SRI project, and also especially Blue Waters, because we have been using Blue Waters since its user-friendly period, and also we use the prac time and Illinois time. So we burn a lot of resources on Blue Waters to get, to do this interesting, problem about graphene and water. So at the end, thank you for your attention, and I'm ready for questions.